I am going to talk today a little bit about running sort of large simulations of galaxies. That is, of course, the topic that is near and dear to my heart, kind of scientifically. And I want to just call out before I even get started that everything I'm going to talk about today is the work not just of me, but of many collaborators, including many students and postdocs. So all highlighted in yellow, these are names of students and postdocs that I've been working with over the past few years, without whom the stuff I'm going to talk about today really wouldn't have been possible. So now that you've all gotten excited about galaxies, I just want to start with a disclaimer, which is that this is actually mostly going to be a talk about software development. So I've actually spent a large fraction of the last 3 years not running large simulations of galaxies, but rather sort of working on code development in order to enable further large simulations of galaxies. And so a lot of what I'm going to talk about today is kind of what was the work that was involved in getting us towards the place that we're gonna try to go in the next few years. So I thought this is probably a safe space to give a primarily software development talk, but nevertheless should warn you in case any of you wanna run away now. All right, so, but I am an astrophysicist, right? And so my motivation does always sort of come back to the kinds of scientific problems that we're trying to solve. And my particular interest is outflows. And so I thought I would spend a little bit of time talking about why I think outflows are interesting, just as a way to sort of lead into the larger problems that we have in terms of sort of software development. And since not everyone here is someone who works on galaxies or outflows, I thought it was warranted to spend a little bit of time talking about why I think they're interesting. All right, so our sort of galaxy formation paradigm at this point in time, right, which is based on a cold dark matter universe, gas collapsing into potential wells, requires stellar feedback, right? And what I mean by that is that we have a whole host of observations without which, without stellar feedback, it's just very difficult to match, right? So the sort of canonical plot, right, of the luminosity function versus the stellar mass of galaxies, right? You can plot up the actual observed stellar mass function, that's the yellow points. And you can compare that to, right, if you just have the sort of, halo mass function and you scale it by the cosmic baryon fraction, you would say that galaxies should have a lot more mass in them, particularly at the low mass end, right? And this is where we appeal to basically feedback due to stars, driving mass back out of galaxies, or at least preventing it from entering galaxies in the first place. Similarly, right, if we look within galaxies in the ISM, a whole range of observations show us that over many orders of magnitude of the sort of surface density of star formation versus the actual, surface density of gas, normalized by the free fall time, right? So basically the number density of gas, right? The volume density, you get low efficiencies of star formation, right? Something like 1% of the gas on a free fall time turns into stars. And again, we tend to appeal to feedback from stars as being responsible for setting this low efficiency on smaller scales, right? Also, metal content, right? So if we look at the metals in galaxies, right? So again, stellar mass of galaxies on the x-axis, and on the y-axis is the mass in metals. And we just look at their star formation histories and we say how many metals they should have produced, right? You get something like this gray line. And in fact, right, we observe in the ISM, in the dust and in stars that the metals are effectively missing, right? And metals are produced in galaxies, right? And so you have to somehow get them out. So again, outflows, right? Sort of similarly, right? If we look in the CGM of galaxies, right? If we look in the halos and even into the intergalactic medium, right? This is just, points again from a sort of canonical paper by Chuck Steidel. Many people have done this experiment, since then in other ways. But if you look out into the halos of galaxies, we see lots of metals, right? These are just rest equivalent widths of a bunch of different metal lines. Metals are produced in galaxies, so you need something to drive them out, and we appeal to outflows. So our sort of canonical model of galaxy formation at this point in time really points towards outflows being a sort of critical component of the galaxy formation and evolution process. Similarly, we observe outflows, right? Again, you'll see I'm a theorist, but I'm very motivated by observations, right? Both in the local universe, right? These are examples of outflows in the local universe. This is more of a nuclear outflow in this star-forming galaxy, and this, of course, is M82, right? Which is a sort of nuclear starburst, more extreme, right? We see stars driving gas out of galaxies, and we see this on sort of small scales. In some cases, we see it on larger scales. If you go to higher redshifts, right, redshifts 1, redshifts 2, where the star formation rates are higher, you find even more outflows, right? So outflows are associated with star formation across cosmic time. And indeed, the data are totally consistent with all galaxies driving outflows at some points in their lives. And so I would argue that we would like to understand this process, right? And the tricky part is that there's a lot of details in here that are difficult to constrain, right? So I've been talking about sort of big picture models. Galaxies have to somehow get gas out, and sort of, individual observations, galaxies can drive gas out. But this is not a straightforward problem to sort of model just from the ground up. Because, right, the sites at which these outflows are driven, which are actual individual star clusters, right, within a star-forming disk, right? This is the beautiful southern pinwheel, again, just a nice nearby star-forming galaxy where we can see what's going on. You can see the nice little ionized H2 regions in red. If you zoom in, right, each of these are individual young star clusters, right? But if you were to zoom in even further, right, this is a young open cluster in the LMC, right? This is the problem. The outflows are being driven on scales of individual star clusters, right? So in other words, if you want to actually know how to drive gas out of galaxies, you need to resolve processes that are on the scales of individual clusters, right? Otherwise, I mean, you can come up with very smart sort of subgrid prescriptions that say for a given star formation rate, how much gas you think maybe should be leaving, but those will not allow you to make predictive quantitative statements about how much gas galaxies can drive out, right? All right, so that's all happening on small scales. And of course, the outflows that we're talking about can be galaxy-wide, right? So this is, again, a nice edge-on spiral where you can see this has nice dust lanes, but these dust sort of chimneys are, again, tracing these sort of outflows that appear to sort of pockmark the whole disk coming from these individual clusters. And of course, M82, which I'll show again, just because you can really see the outflow in this. This is, the H alpha kind of highlighting again, the sort of dust and ionized gas. It's on the scale of the whole galaxy. And so this is, of course, the problem that we always come back to, right? Which is one of dynamic range. You've got to resolve things on very small scales while also capturing things at very large scales. And sometimes the way to do that is by adaptively refining your simulation. But as I'll talk about sometimes, and I think this is an example of one of those times, you actually don't want to just, dump all of your resolution in the disk and leave resolution out of the outflow because you might miss things. Okay, so all of that brings me to what I'm going to describe in the rest of this talk, sort of as a grand challenge problem. And I just want to say that is, this is not terminology I made up. It was terminology that I was required to adopt in order to get to participate in a program that I will be telling you about in this talk. So I don't actually think so much of myself that I have claimed that my problem is a grand challenge and your problems are petty challenges. No, this is that's just, all right. So the grand challenge problem, right, is can we simulate something like a Milky Way galaxy with self-consistent star formation and supernova feedback and a 3-phase ISM, can we do all of that on Milky Way scales, right? So the Milky Way diameter, something like 30 kiloparsecs, the resolution you need to capture these star clusters and the supernova bubbles, right? That's something like a few parsecs. And so the target resolution for this grand challenge problem is something like 10,000 cubed or a trillion cells. Okay. Again, I'm just assuming in this case that we're gonna be doing this at a sort of constant resolution, and I'll try to back up why I think that's important in a few slides. So that's a lot of cells, right? So how do we actually get there? And this is a problem that I've been thinking about for something like 10 years now. So I'm going to tell you all about it, right? And so the first answer is that it's going to matter what kind of hardware we have available, right? This is straightforward. People in this building obviously understand this. But lots of problems in astrophysical simulation have this issue. You require sort of extreme dynamic range in order to fully capture the physics that you're interested in that's kind of driving your problem. So galaxy evolution, I've been talking about outflows and star formation. Obviously, star and planet formation has this problem, AGN feedback, etc. And I also just want to say, I often frame this in terms of a problem of dynamic range, right? How many cells are required, et cetera. But it's very much also a problem in the dynamic range in time, right? If I want to actually, on small scales, resolve what's happening in a hot supernova bubble, I have to take very small time steps because the gas is very hot and it's moving very fast, right? And now, I need to take time steps of 10 or 100 years in my simulation that I want to run for a gigayear, right? So you not only have to be able to do sort of high spatial resolution, you also have to be able to go really fast so that you can afford to run for a long time. And so there are various different strategies to approach all of these problems, right? All of them sort of relevant and useful in their own way. The most common, I think, in our field is some sort of adaptive refinement scheme, right? So either a mesh that refines adaptively so that you can get to smaller scales by sort of dumping your resolution where you think you need it the most. That's usually a sort of mass resolution target, right? That's what sort of Lagrangian particle schemes do naturally. They dump all the resolution where all of the mass is. Increasing resolution, of course, is another strategy and the one that I'll be talking about. But also just redefining the problem, right? Sometimes, even with all of the power of an exascale computer or an adaptive code or what, you're still not going to be able to do this, and you need to think, even more sort of outside of the box, as it were. So, what's required in order to increase the resolution in a simulation? Again, I'm going to talk about a static mesh code because that's the most straightforward case and the one that I'm applying. But basically, if you have a static mesh, right, so you have a three-dimensional grid full of cells, and you want to double the resolution, right, so have the size of the cells in each of these three spatial dimensions, that automatically costs 16 times more in compute time, right? So you get 3 factors of 2 just from the number of cells you've added, and then you also lose a factor of 2 in the time, right? Your time steps get cut in half. So adaptive methods, of course, increase resolution by adding particles, right? Or decreasing the mass of an individual particle. And that works really well in situations where you want to spend all of your compute time in the highest density regions. But it suffers from a sort of key problem, which is that not all densities are going to be resolved equally. And so again, one reason that I think that a sort of finite spatial resolution is important for the kinds of problems I was describing earlier, ISM, supernova remnants, outflows, is that it's sort of critical that we resolve the hot phase of the gas. And the hot phase of the gas is very low density. And so if you require a constant mass resolution in your code, the way most adaptive methods do, you'll never resolve the hot gas, right? You just really have to go to crazy small mass resolutions before you start to resolve the hot gas. And so a sort of valid strategy is actually just to fix the spatial resolution of your simulation, and that will, by definition, mean that you will resolve the hot gas. So if you think hot gas is what's driving your outflows, you want to make sure that you're actually resolved. All right. The good news is that increasing resolution is something that is a totally feasible approach, as demonstrated by, for example, this plot I made that's probably out of date now. But this is just a plot as a function of year of different. These are mostly cosmological simulations that, I just picked cosmological simulations that ran down to redshift 0. And on the y-axis is the resolution elements, right? So how many particles or cells roughly are in the simulation. And what you see is, over the course of the last 25 years or so, the sort of largest cosmological simulations have increased in resolution by something like 6 orders of magnitude, right? Meaning that simulations with something like 10 billion resolution elements and complicated physics, right? So gravity and hydrodynamics at a minimum, right? But some of these simulations also include, a lot more, are now sort of feasible, at least if you have supercomputers, right? That is not a coincidence, I think, in the sense that the peak speed of the world's fastest computers has also increased by roughly 6 orders of magnitude in the last 25 years, right? In other words, astronomers have been doing quite a good job of taking advantage of the machines that are being given to us, right? I don't want to ignore the fact that a lot of algorithmic work went into making sure that those simulations could run on these machines, right? That's part of what I do. And indeed, the simulations that were being run in 1996 are really different in terms of the code than the simulations that are being run today. Nevertheless, right, it's the sort of power of the machines that has driven a lot of our algorithmic development. And to get a little bit more fine-grained, the power of those machines is driven by increased hardware parallelism, right? So what I mean by that, if you've ever seen a plot like this is again as a function of year. It has various numbers on the y-axis here, depending on which of these points you're looking at. But the trend I just want to point out is that, this sort of well-known clock speed top out that happened in the early 2000s has meant that since then, basically all computing architectures have gone to adding parallelism, right? Number of logical cores here, just meaning, right, we used to have 1 core CPUs, now we have 128 core CPUs, right? And the trend, that trend has also included going to sort of even more parallel architectures than this, right? i.e. things like GPUs and graphics cards. So what has that resulted in? That has resulted in these supercomputers that have also been increasing their sort of peak computational performance by, again, something like 6 orders of magnitude over the last 25 years. So here's years, here's the peak speed in teraflops of computers as they've topped the top 500 list, right? Which is just a list where computers have to meet certain benchmarks that demonstrate that they actually have this speed, right? Of course, a lot of the benchmarks used to put points on this plot are not particularly, what do I mean? They're somewhat specialized, right? In other words, you run a particular linear algebra library and demonstrate that your computer can reach this sort of peak theoretical performance. That's very different than running a complicated astrophysics simulation, right? And so much of what I'm going to talk about is fine in Frontier, Frontier, which is the new Exascale computer at Oak Ridge, right? Here's our Exascale line. They broke it. Good for them. No, that was, obviously that also is an achievement. It's been like decades in the making. But they broke it by running, sort of specialized libraries and that kind of thing. And so actually making sure that we had like real physics codes that could run on that machine is most of what I'm going to talk about for the next 20 minutes or so. All right. So a little bit more about Frontier, because Frontier is going to be the sort of star of this talk. So Frontier is an exascale supercomputer that was installed at Oak Ridge National Lab. It did officially get to the top of the top 500 list on June 1st, 2022. And I just do want to say that was a major achievement on behalf of the engineers and the people that built this thing and the Oak Ridge staff. Because as you can imagine, right, this supercomputer was being installed during a pandemic. If you heard about supply chain issues, you can imagine how difficult it was to just even get basic parts to put this thing together. I think a lot of people worked really hard, and that was a really amazing achievement. And so its peak speeds are something like 1.1 to 1.5 exaflops. Maybe they've gotten it up a little higher at this point. And it is mostly powered by GPUs. Right, so this again is a trend in supercomputers. That these days, the sort of heaviest lifting is usually being done by GPUs. And so a Frontier node has 1 AMD EPYC CPU and 4 AMD EPYC GPUs per node. Yeah, is there a question?
Can you repeat the question?
Yes, so the question was, I think, how do you compare AMD EPYC GPUs to NVIDIA A100s? Or yes, and so the answer is that AMD, like NVIDIA, has various scales of GPUs, and so the ones that are on Frontiers are called MI250X, and I think those are quite comparable to A100s. They have comparable memory, they have comparable numbers of logical cores, yeah, and we see comparable speeds out of them. Yeah. Yes, and indeed, right, the other thing that's nice about this computer, right, is that it's a national resource. It's allocated through national calls for proposals. They have a really robust director's discretionary time program. And so it's actually a pretty easy place to get started on computing. You all, I think, are very spoiled. You have all your own in-house computing, but that's I think also just something to keep in mind, right? These are publicly available resources. All right. So what I actually am gonna again spend the next 20 minutes or so talking about is what we did to sort of prepare to run on Frontier. And so this was done through a sort of special program. So we did get some special privileges, although we did again apply for them. And the idea was that Oak Ridge and the people that are funding these machines recognize that in order to kind of fully leverage them, they need to have software applications that are ready to run on them when they turn on, right? There's a lot that goes into making sure that you actually can run efficiently on a machine like this. And so Oak Ridge and the Exascale Computing Project put out a call a few years ago for application teams that were sort of interested in optimizing their code for Frontier, right? And so our group was one of the groups that was selected to take part in this. The Oak Ridge branch of this is called the Center for Accelerated Application Readiness, or CAR. And the application, of course, that we were going to target is our GPU-based astrophysics code, Choya. So in case there's anyone here who doesn't know what Choya is, I am not so impressed with myself as to think that everyone here knows what Choya is. So Choya is, as I said, a GPU native, massively parallel, finite volume hydrodynamics code. So I started developing Choya roughly 10 years ago when I was a PhD student at Arizona. So Choya is actually an acronym that stands for Computational Hydrodynamics on Parallel Architectures, where parallel at that time, I left it somewhat agnostic, but it was originally intended for GPUs. It's also, a type of cactus that grows in the Sonoran Desert. Actually, there's like 200 different species of Choya, and they all have their own unique quirks. Some of them attack you. Anyway, some of them are very nice, right? Think teddy bear Choya. All right, and so Choya is a publicly available code, right? You can get it on GitHub, and all of the development work I'm going to talk about today is in the public code repository, although not all of it is in the main branch, right? Some of it is still in the development branch. All right, brief refresher. in case people here are used to thinking about things in terms of finite, in terms of like SPH or particle-based kind of hydrodynamics, or maybe you work on, Gaia data and don't have to think about hydrodynamics codes very often. So by finite volume, I just mean when we run a simulation, we divide it up into a grid of cells, and the main work of the hydrodynamics solver is to take sort of average values of conserved variables in each cell, density, momentum, energy, those are the conserved variables, calculate fluxes of those variables through each cell interface, right? And use those fluxes to update the average values to the next time step, right? One of the reasons I point this out is because one of the reasons that we had the idea to write a GPU-based hydrodynamics code in the first place is that this is a very local problem, right? You are solving locally for fluxes on cell interfaces, and this cell doesn't care at all about what's happening in this cell. And so it immediately seemed like this would be a good target application for an extremely parallel code. And indeed, that hypothesis turned out to be right. So we originally were developing this for Titan. A lot of the work I'm going to talk about today actually took place on Summit, which was the biggest GPU-based supercomputer at Oak Ridge until they installed Frontier. And the idea is quite conceptually simple in its framework, which is just that a GPU, right, you have some global memory, and then the sort of logic of GPU programming is that you have millions of individual threads, each of which are divided up into larger blocks. And those blocks are distributed by the GPU itself onto all of the available cores. So a GPU might have thousands of cores, but you can have millions of threads that you assign. And your programming model is largely agnostic to sort of how many blocks the GPU can run at once, right? And that's very nice because it meant Choya's fundamental prescription of assigning cells to threads hasn't changed, even though we've gone through many generations of GPU hardware. All right, so that's the idea. We assign GPU threads to cells, and you get this sort of fine-grained parallelism, just sort of by nature of how GPUs work. All right, Choya has undergone a lot of development in the last few years, even aside from the project that I'm going to be talking about, which is this car project. And I have to call out in particular the work of Bruno Villaseñor, who was a graduate student at UCSC. Now he works for AMD. And Bruno was interested in running cosmological simulations with Choya, so big fixed grid cosmological simulations to learn about the Lyman alpha forest. So he added a lot of stuff. In other words, when I finished graduate school, Choya really was a hydrodynamics code that maybe could do some cooling. And Bruno added a self-gravity module. So our primary self-gravity module is an FFT-based module, but there's also a relaxation method. A particle solver, which he wrote originally for dark matter, but we've updated it so you can use it for things like star particles. A non-equilibrium chemistry and radiative cooling module, think something like Grackle. A UV background, a co-moving coordinate system, right? In other words, everything you need in order to run big cosmological boxes. And later in the presentation, I'll show you some of Bruno's cosmological boxes. They are very beautiful. All right, and so that's just to, when I later show you plots that have all these other physics on them, and I've only mentioned hydrodynamics, that's where it came from. So how does it all work? This is how Choya worked in 2019 when we started the car project. This is basically the code that existed from how I wrote it when I started writing this code in graduate school. You have a simulation domain. You divide your simulation domain up into subvolumes. You assign each subvolume to an individual GPU. Basically, each MPI rank gets a GPU. And a typical subvolume was something like 128 cubed cells. That's basically based on how fast the GPUs can process the data. Each cell, as I said, maps to a single thread. So when you launch your GPU functions, you're launching them for that whole sort of subvolume at once. And something that was useful at the time, subvolumes could be further divided. In other words, I could split this subvolume up if their size was too big to fit in the GPU memory, right? And that was because at the time, GPU memory was maybe 2 gigabytes or 6 gigabytes, and CPU memory was way more than that. And so maybe you could fit, 128 cubed cells on the CPU, but you couldn't fit that many on the GPU at a time, and so you had to divide it up further. And then the sort of, progression, the idea was you have your sort of fundamental data sitting on the CPU, right? You initialize all of your cells, you set the boundary conditions, and then you transfer the data over to the GPU and run through the Hydra model and transfer it back. And then you can output if you need to, right? And this was the at the time, sort of prescription for GPU programming. You offload the heavy parts of the calculation to the GPU. And indeed, even when we sort of started that project in 2019, there were also some of these new physics modules that Bruno added that executed partially on the GPU or even totally on the CPU. And this was, again, a sort of useful thing to do at the time, because you could have the GPU working on one piece of physics while the CPU was working on another, right? And it seemed like a good idea. But so fundamentally, our grid sort of lived on the CPU. And the first thing that we had to address when we started working on the car project was that this model was not going to work anymore. And the main reason is this, right? These data transfers were just taking way too long. And so we were sort of losing out on the actual power of the GPU because we had to send all of this data back and forth. All right, I think I should have put this slide probably earlier, but just to mention, one thing that made the car project really successful, I thought, was the fact that the team was, it wasn't just astronomers or just sort of software engineers, but it was really a sort of integrated effort of, these are all of us working at Pitt, some of the folks working at Santa Cruz, but also, Oak Ridge staff, and vendor partners, so Trey at HPE, Damon Dougal at AMD, and these people really did contribute a lot to the project, and so that made possible some of the things that we did. All right, so what did we do? So the car project had one sort of task associated with it, and that task was that we were supposed to hit a figure of merit, or FOM, on Frontier, and the figure of merit was supposed to be 6 times our original performance on Summit. All right, so that's not too bad. The thought being that Summit was a 200 petaflop machine, and so if you could hit 6 times your performance on Summit, then in theory you're running at Exascale, right? So for our figure of merit, or FOM, we basically just ran a cosmological simulation, a very simple box that Bruno had set up for us that used all of the relevant physics modules we would need for this grand challenge galaxy simulation that I've described. There was some stuff that we still needed to do on the galaxy front, but we wanted to make sure we understood, for example, how the Poisson solver, the FFT scaled, how the particles scaled, how the MPI communication scaled with all of these physics modules and then the Hydra, right? And so this is our weak scaling plot as of the beginning of the project, number of GPUs on the x-axis. This is Summit, so we're already talking about a lot of GPUs over here, and this is our sort of speed in terms of milliseconds per some volume, 128 cube cells per GPU. There were basically 3 challenges that I'm going to outline that we had to overcome in order to get to our sort of target figure of merit. The first was actually performance portability, right? So Choya was originally written in C++ and CUDA with MPI for sort of off-node parallelism, and then maybe a little bit of OpenMP thrown in there just for fun. Why not? At that point, it's already so hard to compile. Make it a little harder. And so Frontier has AMD GPUs, and those use HIP. So if you're not familiar, HIP is more or less the same as CUDA. It has basically all the same functions, but it's AMD's version, and AMD's HIP-CC compiler can compile HIP code for either NVIDIA or AMD GPUs. So the solution that was first presented to us was basically just translate all of your source code into HIP code, and then you can compile. And we did do this, and it did work, but I didn't love it because there's no reason that an NVIDIA-based computer would have HipCC installed, right? And so we actually went with a slightly different route. So I'm just, I don't know, mentioning this in case anyone has CUDA code and they want to run it on AMD GPUs. And we called this HIP-a-fly or HIP on the fly. I accidentally X'd out of my presentation somehow. And the idea is that we actually just have one header file called gpu.hpp. And if we've defined in our make file that we're going to compile for AMD GPUs, this header file redefines every CUDA call as the relevant HIP call. And so all we have to do is if you add some new CUDA code that has some function in it that we haven't gotten in here, you just add it in here. And now we have like one single CUDA code base that is in fact performance portable to AMD GPUs. And I think this is nice. There's still a lot more, for example, just documentation and examples out there on the internet of CUDA. CUDA was one of the earliest GPU programming languages and paradigms. So we were happy with this solution. All right, the second challenge, as I already alluded to, is the fact that we needed our data to live on the GPU. So originally we offloaded it for every time step so we could have bigger grids. But as the GPU speeds have increased, these CPU to GPU communication speeds have stayed roughly the same. In other words, the performance of the GPUs has gone up by at least an order of magnitude, if not more, since I started this project, and the speed of like the PCI bus has gone up by much less than that, right? And so we were in the situation, right, where data transfer was basically taking up a larger portion of every time step than the hydrodynamics calculation. And so we were losing a lot of the power of the GPUs. So of course, the solution was just to keep the grids on the GPU, transfer our boundary cells using GPU-aware MPI. I'll get later into why that was important, and basically only transfer the grid back to the CPU for output. This does have the limitation, right, that we are restricted by GPU memory. GPU memory has gone up a lot, right? These new cards have, 64, 80 gigabytes of memory. It's still usually less than the CPU, and so this won't be a solution for everyone, but it was definitely a solution for us. And just doing this alone resulted in a sort of something like a 4 times speed up for our hydrodynamics. The third challenge we had was gravity. And this is where I was really glad that we had some vendor partners who were psyched to do some sort of programming, because we had this gravity solver that was based on FFTs, and we have a block-based domain decomposition. And so that means we just needed a block-based FFT library in order to do our Poisson solve. And when Bruno wrote the code, he did this with, to our knowledge, one of the only sort of block-based public FFT libraries, which was PFFT, but PFFT was a CPU library. So even if we were actually running the Fourier transforms on the GPU, we still had to be doing a lot of this work on the CPU because that was the library that we had access to. But Trey really stepped up and just wrote us a new block-based Poisson solver, which he called Paris. And it is also hardware agnostic. It can use QFFT or RockFFT, depending on the GPU. And it does everything on the GPU. It performs its FFTs, it does GPU direct MPI communication, et cetera. Again, we saw something like a 4 times speed up in the gravity solver, just on the same hardware by making this change. Say a couple more words about Paris, because I don't know who's here or what you're interested in, but it is like a kind of a standalone solution that may be useful if you're the kind of person that does FFTs. Paris moves everything to the GPU, right? So the FFTs are very fast. It does the Poisson solve in frequency space. You've got MPI communication, et cetera, right? It's a distributed memory algorithm. And it's available at this GitHub repository where Trey has it as kind of a benchmark. If you want to like see it in a code, right, you can of course look at it in Choya where it's sort of integrated to do the Poisson solve. We're also later going to use it to do some of our radiative transfer. And something else that's kind of neat about it is that unlike a lot of FFT solvers, Paris can deal with open boundaries or analytic boundaries. So this was another problem for us when we started, because most FFT solvers are designed for periodic boundaries, which is great for things like cosmological simulations and not great for things like isolated galaxy simulations. So this was one of the reasons we couldn't run a FOM with a galaxy, because we had no way of dealing with gravity at the boundaries. So Paris can do this. You can put in an arbitrary analytic function for the boundaries by converting discrete sign transforms. Anyway, Trade really did, I think, us a huge service in putting this together, and it's something that, in principle, can be used for other projects. And so I just wanted to highlight it here. All right, so putting all that together, how does Choya work today? We had a couple more things we had to do. The particle solver also wasn't totally on the GPU, so we had to move it. Packing our boundary buffers on the GPU and sending things off node using this GPU aware MPI made a big difference, because not only were we now packing all of our buffers in parallel, but also, this is my new sort of schematic. One thing you'll see is up here above the CPU line, there's very little now. We basically just set the initial conditions. And if we want to output, right? So the grid data lives on the GPU, we can transfer it back if we want to output. On machines like Summit, the boundary data, those MPI buffers, does still have to move back across the CPU-GPU interconnect. But Frontier has network connected GPUs. And so with this sort of GPU-aware MPI, we never have to send even the boundary data back to the CPU. It just goes straight out to the network. And that also makes things faster. So cool. So yeah, so that's basically the idea, right? Everything just happens on the GPU now, and we only send stuff back to the CPU if we want to output it. So where did that get us? Our total performance gains. All right, so our overall performance on Summit at scale, right, is a factor of about 4, and that's just from algorithmic improvements, right? So that's the move that we made, right? We went from up here, right, to down here. So that was great. And then on Frontier, right, this is sort of hot off the presses scaling plot from a few weeks ago. We also get more improvements in speed from these network connected GPUs, and the fact that the hardware, there's just more GPUs and they are faster than the ones on Summit. So in the end, we did hit our sort of target FOM. We got a total performance gain of about a factor of 20. And that, that was great. That's kind of what we're aiming for. And so at this point, I mean, this is, I think, about the best that you can do for hydro plus gravity on machines of this scale. I've seen there's a couple other applications that have done hydro or various problems, and we see sort of comparable performance. All right, so obviously our next task is to run this grand challenge simulation that we proposed, this simulation of the Milky Way with sort of parsec scale resolution. We have started sort of test runs with our disk setup. This scaling plot is with the full disk setup going out to 10,000 cube cells. And it looks good, but we did just get on the machine ourselves a few weeks ago. So we haven't, I don't have an amazing galaxy simulation to show you today. All right, so that's kind of wrapping up this part. Since I have 8 minutes left, I want to show you a few other things that we actually have done with Choya in the past few years, just to give you a sense of kind of what we're actually doing with the code outside of this sort of software development. So first, I promised to show you some of Bruno's simulations. So Choya has been used to carry out hundreds of massive, where massive means something like 2048 cubed, cosmological simulations on a static mesh. And this is a visualization from one of Bruno's simulations. He makes very beautiful visualizations. This is all his sort of own homegrown code. And the ultimate goal is to sort of more accurately model the Lyman alpha forest, eventually in kind of hopes of constraining cosmology, I think related to kinds of efforts that go on here. In the course of this project, Bruno actually, he's graduated now, and so these papers kind of constituted his thesis. But he discovered some really cool things. So, for example, Bruno was able to basically brute force come up with a model for hydrogen and helium reionization heating that matches the sort of best available data which is, so sort of you think of like Hart and Maddow, right? But we know there were sort of problems with the heating rates in the Hart and Maddow. People have come up with other sort of models that also, we were able to test. And Bruno basically just said, all right, whatever with the models, I'm going to run a grid with hundreds of cosmological simulations that resolve the Lyman alpha forest and the temperature structure, and just figure out which simulation matches the data best. And it's sort of a parameterized model of free ionization heating, which is, I think, very cool, and something that could be applied immediately, right, in other codes. And also, I was on a paper, I never thought I would be on a paper about dark matter. So Bruno carried out some simulations looking at the mass of a warm dark matter particle and was able to show, again, with this sort of parameterized grid, matching it to the Lyman alpha forest data, he was able to sort of put a limit on the mass of a warm dark matter particle, basically just by showing how it wipes out the fine scale structure in the Lyman alpha forest. These are more extreme, right? The actual limit is between these two simulations, but you can't see it. So show all four of them. We want to do this better. So to do that project better, we need radiative transfer. And Choya can do radiative transfer now. So in a parallel effort, we've been adding a radiative transfer solver. It's based on Nick Nedden's OTVET method. So this is I know it looks not that amazing compared to the simulations you just saw, but I'm very proud of this, propagating ionization front, right? And so this is, fully coupled radiative transfer with hydrodynamics, and it's very fast because, again, it's all done on the GPUs. Choya also is MHD now. So one of my PhD students, Bob Caddy, has implemented a magnetohydrodynamics solver that uses constrained transport to evolve the magnetic field. Here's his Brio and Wu shock tube, right? That's sort of notoriously challenging shock tube. And it has, sort of both second order reconstruction and third order reconstruction. It works beautifully, right? Here's our convergence plot. So the second order PLM method converges at order squared, and PPM, because the integrator is second order, also converges at order squared, but you get slightly better, slightly better errors. I'll also just highlight that Bob added an extensive test suite to Choya, and I think critically an automated testing framework, so that now when someone submits a pull request, it doesn't just break everybody else's code. I think this is absolutely fantastic, and it's going to make it much easier for us to have a really sort of community-driven development effort. And so that's just he should be commended for taking that on, because it was a real lift and is paying off. All right, I'll show one more thing. It's the fun thing about having students, right? Is they start doing things and then you can show what they're doing. So I have another PhD student, Helena Ritchie. She's been implementing a dust model into Choya. So starting with just kind of sputtering, right? You hit a dust grain with an electron and you start to ablate it, right? And accretion, right? You can kind of stick metals onto dust grains. And this just kind of uses our existing passive scalar framework, but we're planning to expand it potentially to include other mechanisms, shattering, coagulation, whatever you might like. And right now she's using it to do idealized simulations of winds. So this is your dense cloud in a low density hot wind. This is the gas density. This is the dust density and projection, right? And we run this. So I'm back to doing cloud wind simulations where it all started, but now with dust. And so we're trying to explore, when and how dust survives or gets destroyed in galactic winds. I'm finding some interesting things, so ask me about this if you're interested in dust in winds or in the halo. And we, of course, plan to do this all on sort of galaxy scales. So future directions, where do we want to go? Of course, the goal is to run these massive isolated galaxy simulations with all of this cool physics that we talked about. We can now run these sort of trillion scale cell simulations. And so in principle, we should be able to do this sort of consistently resolve star formation feedback cycle. I'm really excited about what we could learn about, if the Milky Way is driving a wind or if there's a fountain, right? This is all the kind of thing that you can resolve if you have a sort of global scale simulation. And of course, we want to do all of our experiments with all these other things. And the nice thing about the GPU is that additional work is relatively cheap on the GPU. And so all of these things are sort of feasible. And radiation, well, we wouldn't be able to do it at 2 parsec scales, but we could probably actually manage to do a sort of galaxy scale simulation with radiation at interesting resolutions. So, all right, I'm out of time, I think, so I will finish with that and say thank you and show you one of my old simulation movies that I always show to distract people so that they don't ask me hard questions. But that's it. All right, thank you.
I'm distracted.
I was gonna say.
Okay, Eric, start us off. Yeah, let me. Whoops. Here, ceiling mic should now be on. So you're.
I saw that you had a really dramatic improvement in the time you were spending on your particles as well, but you didn't get so I was just curious how you achieved such a dramatic speed up there.
Okay, well, I have 2 answers. The first is that you actually caught me out on something that I wasn't paying attention to when I put together this talk, which is that one of the scaling plots has particles where they're sort of the same number of particles as grid cells. Those are the cosmological ones. But then the later ones actually have a totally different particle model where the particles are star clusters. And it turns out if you have thousands fewer particles, it runs much faster. But we did also see improvement. The particle solver was implemented in part on the CPU because that's where all the gravity was. And so when we moved particles over, we did see an improvement, but not as drastic as what you were seeing.
That looked crazier than anything else.
Yeah. No. But no matter, I mean, it's always been the case that the particles are a very subdominant part of they're much faster than the rest of the modules.
So you didn't change much about that?
We didn't change very much about the particles, yeah, other than making sure that they were on the GPU.
Okay, any other questions? Shirley?
I was really impressed with the very, very flat scaling as we go in number of GPUs. I'm curious what's left there. Is it all just communications?
Yeah, so going back to like this plot or
they're all really flat.
Yeah, I mean, so right, if you look at this, right, I mean, our total weak scaling is pretty flat. The hydrodynamics sort of by nature is always going to be very flat because we're only counting the sort of local problem. And so if the hydrodynamics is going up, that just means that you've got a problem with your GPUs, right? And some of them are taking longer for reasons you probably don't understand. You can see that there is this transition point, right? So our Poisson solver starts at small scales, taking less time, and by the time you get up to large scales, it dominates the calculation. This is actually something I'm interested in. Like for a fixed grid code, FFTs work well, but we do also have this relaxation method, which on these scales is definitely going to take longer than the FFT method. But on these scales, the relaxation method's probably faster, right? So this is where things like multi-grid come in. And so we may try to actually improve that by switching the gravity method up to. The MPI communication, not surprisingly, doesn't weak scale perfectly, right? It does go up as you increase sort of size of the network. And then this line, yeah, I mean, this line it's not real. This is hot off the presses, like I said, and I didn't get through all of it, but yeah.
Great. I think, yeah, why not Lehman first?
I was wondering how you debugged this code as you were developing it, because debugging code is hard, debugging GPU code is harder, debugging parallel GPU code is really hard.
Yes. So indeed, there's always a sort of multi-step approach, right? Where you you start with you know, sort of the least parallel problem you can and work your way up generally when you're debugging, so that you can kind of convince yourself that a problem that didn't show up on one GPU but does show up on 4 GPUs probably isn't a problem in your physics module, right? But has something to do with. But one thing I will say is this is an area where, you know, like this sort of automated testing framework is making a big difference, because, I mean, now at least if you break something, you can tell, right? And so if you are being a good developer and doing continuous integration and making lots of commits, that does make the debugging easier, right? And that's, I mean, one of the reasons that we went to this sort of model is that it dramatically changed the effectiveness of coding as a team, right? It just used to be the case that, you know, someone would just send me a huge pull request every 6 months or every year, and that's a disaster, because then when something else is broken, you just have no idea what broke it. And now we really do kind of go for really small commits that we can immediately sort of test. And the main challenge is that not all of our code is actually covered by tests yet, but we at least have regression tests for all the sort of major physics, and that helps a lot. After that, I don't know, people have different, you know, their favorite debugging strategies. I've heard good things about, you know, ARM as a sort of parallel debugger. So Bob really likes the ARM debugger, which is capable of doing GPUs and sort of parallel simulations. There's other ones that the sort of HPC folks have been working on. I'm just totally lame and still use printf all over the place. But if you understand the structure of the GPUs well enough, it's still a really powerful tool, right? So yeah, there's no one answer, I guess.
Okay, just I was missing things, so let's go to the classroom quickly if they can try to chime in.
Yep, I have a question. Can you hear me?
Yes.
Perfectly.
Yes. So I saw this week scaling is amazing, but how do you determine the time step for the test? I mean, the weak scaling, it determines the number of communication for the power computing. But how did you decide the time scale or time step in the simulation?
So for our weak scaling plots, we always do the same thing, which is we run a problem, whether it's a cosmology problem or a sound wave, or in this case, a full disk with self-gravity, et cetera, right? Just, this is not with feedback, but this is just our sort of fiducial disk setup. We run it for, you know, enough time steps that the sort of average is plausible, right? So 100, couple hundred time steps, and then we just divide out by the number of time steps, and that gives us this number, right? Milliseconds per 256 cells per GPU. So does that answer your question? Like this just is, if you have 256 cubed cells on each GPU, this is how long a time step takes. Which is different than how long the total problem takes, right? How long the total problem takes depends on how many steps we take. But this number doesn't change as you increase the length of the problem, because it's just how long does a time step take.
Yeah, thank you.
Last one.
So going back to the amazing destructive movie in the end. So now with the new DAS model, because you mentioned you're planning to run like wind simulations with the DAS. I was wondering if you have a sense already of whether there's going to be like DAS lifted by a wind with those similar conditions as in your field simulation, or
Of course, it's gonna look like this. It's gonna look just like this. But no, actually, I mean, I do think, like, I hope, right, that like what you will have is this sort of disk with all of these little star forming regions, and like I anticipate see the dust behaving kind of like this, right? It preferentially is in the sort of dense gas, and that does get lifted out. The dense gas in our sort of older wind simulations tends to not get too far, right? And so assuming that most of the dust is sort of sitting in the dense gas, at least most of the kind of optically thick stuff, it would probably look something like this, where you have some scale height that's just set by kind of the star formation rate. But I don't know, we haven't actually done it.